Welcome all to today's lecture. Myself, Assistant Professor Tukur Gupta from Ajay Kumar Garg Engineering College, Ghaziabad. And the subject that I am covering in my lectures is microprocessor and microcontroller. Subject code is KEC 502. Today, I will be covering 8051 microcontroller architecture. So when we talk about the basics of 8051, it's very popular 8-bit microcontroller introduced by Intel in the year 1981 and has become almost the academic standard nowadays. So 8051 is based on 8-bit CISC core with Harvard architecture. Its 8-bit architecture is optimized for control applications with extensive Boolean processing. The point to note is it's a 40-pin DIP chip, that is dual inline package chip, and works at plus 5 volts DC. So when we talk about the salient features of this microcontroller, so 4 kilobyte on-chip program memory, that is ROM, or particularly we can say EEPROM, that is erasable programmable read-only memory. 128 bytes of on-chip data memory, that is RAM. So basically, we are having 4 KB of ROM and 128 bytes of RAM. It is having 8-bit data bus, 16-bit address bus, 32 general purpose registers, each of 8 bits. So these general purpose registers are all of 8 bits. There are 2 timers, 16-bit timers, T0 and T1, 5 interrupts, that is 3 internal and 2 external, 4 parallel ports, each of 8 bits, and they have been named as port 0, port 1, port 2 and port 3. So these are 4 parallel ports. So in total, since there are 4 ports and each of 8 bits, 8 lines, so there are total 32 lines. One 16-bit program counter and one 16-bit DPTR, that is data pointer. One 8-bit stack pointer, which we call stack pointer. Program counter we call as PC and data pointer by DPTR. 1 microsecond instruction cycle with 12 MHz of crystal frequency. 1 full duplex serial communication port. The architecture can be portrayed as shown here. So this is ALU unit with A and B type of registers. 1 program counter of 16-bit, DPTR. This is the 16-bit address bus, 8-bit data and address bus. PSW means the flag register. Special function registers are there and which have been allotted the RAM for this special function registers. ROM is of 4 kilobytes. These are 4 ports, each with different pins. And we will discuss these ports in detail in further lectures. So basically it has Harvard architecture with CISC concept. Harvard, we all know that the memory space for code and the data are different in Harvard architecture. CISC concept means it's having the complex instruction set, means a single instruction can execute multiple operations. The block diagram is shown in the figure. In next slide, I'll show you the block diagram, which consists of these main parts, that is 8-bit ALU, 1-bit PSW, 1 8-bit PSW, A and B registers, 1 16-bit program counter, 1 16-bit data pointer register, DPTR, 128 bytes of RAM and 4 kilobytes of ROM. 4 parallel input-output ports, each of 8-bit width. So this was the block diagram. So when we talk about the A and B registers, ALU is associated with these two registers. A and B registers are special function registers which hold the results of all the arithmetic and logical operations. The A register is also called the accumulator, as its name suggests, and it's used as a general purpose register to accumulate the results of the large number of instructions. By default, it is used for all the mathematical operations and also data transfer operations between CPU and any external memory. The B register is mainly used for multiplication and division operations along with the A register. So, in few instructions, these are used in combination. For example, in multiply operation and in division operation. So, we will see these instructions in detail in subsequent lectures. Now, when we talk about the R registers, these are the set of 8 registers which are named as R0, R1, R2, R3, R4, R5, R6 and R7. So, R0, R1 up to R7. These registers are used as auxiliary registers in many operations. R registers are also used to store the temporary values. So, basically 8051 is divided into banks and each bank is having 8 registers which are named as R0 to R7. Program counter is a 16-bit program counter. It always points to the address of the next instruction to be executed, as we all know. Similar to 8085 and 86, here also the program counter is always holding the address of the next instruction to be executed. After execution of one instruction, the program counter is incremented to point to the address of the next instruction to be executed. So, it is the contents of the PC that are placed on the address bus to find and fetch the desired instruction. Since the PC is 16-bit width, 805 can access program addresses from this to this range. So, that is total of 64 KB of code. Now, what is a stack pointer? It always stores the address of the stack top. That is, the stack pointer is used to indicate where the next value to be removed from the stack should be taken from. When the value is pushed onto the stack, 8051 first increments the value of stack pointer and then stores the value at the resulting memory location. Similarly, when the value is popped off, 8051 returns the value from the memory location indicated by stack pointer and then decrements the value of a stack pointer. So, we can conclude that in the stack, as you go up, that is, some data is stored in the stack, then the stack pointer value increases, and when we pop out, the stack pointer value decreases. Since the stack pointer is only 8-bit wide, it is incremented or decremented by 2. So, it is modified directly by 8051 by 6 instructions, that is push, pop, ACALL, LCALL, that is absolute call and long call, return and RETI, that is return from interrupt service routine. So, this is the special instruction which is used in case of the interrupts, when we are using interrupts. So, it is also used intrinsically whenever an interrupt is triggered. So, what is a stack in 8051? It's a part of RAM and it's used by the CPU to store information temporarily. This information may be either data or an address. The CPU needs this storage area as there are only limited number of registers. So, we need a stack. The register used to access the stack is known as a stack pointer, as we have already discussed, that is always holds the address of the top of the stack. So, it can take the values from 00 to FFH. So, when 8051 is powered up, the stack pointer register contains the value 07. That is a RAM location. 808 is available as the first location being used for the stack. So, we have to note it that as soon as the power is on, the default value of a stack pointer is 07. So, the first memory address available in RAM is 808H. So, the two important instructions used to handle the stack are push and pop. So, we can see here, suppose I am writing move R6 comma hash 35. Hash indicates that is immediate data. So R6, in R6 I am storing 35H. Now suppose I am writing R1 hash 21. So in R1 I am writing 21H. Now I am writing push 6. 6 here means R6. So it means the contents of the R6 will be pushed onto the stack. Again I am writing push 1. Push 1 means the contents of the R1 will be pushed onto the stack. So now as a conclusion, the RAM location 08 to F1F can be used for the stack. If any program we need more than 24 bytes of stack, we can change the stack pointer locations from 30H to 30 to 7FH. This can be done with the instruction. Suppose I am moving some data in the stack pointer, it means the value of the stack pointer is being changed. That is, I am changing the address of the top of the stack. So in this way, I can relocate the stack. So this is how we can change the location of the stack to be used. Now, when we talk about the DPTR, it's a 16-bit register and it is the only user accessible register and it's used to point the data. So when 8051 accesses external memory, it will access external memory at the address indicated by DPTR. This DPTR can also be used as the two 8-bit registers, that is DPH and DPL, that is data pointer higher order byte and the data pointer lower order byte. Now, when we talk about the PSW, that is the program status word, which is similar to the flag register. And so it's mentioned here, in the 8-bit register only 6 bits are used by 8051. The 2 unused bits are user definable bits. In the 6 bits, 4 of them are conditional flags. These are carry, auxiliary carry, parity and overflow. As we already know that these flags indicate some condition of the arithmetic and logical instructions which have been executed. So here bit number D0 to D7 indicates carry, auxiliary carry. Then again it is the overflow now, and this is the parity. So these 4, carry, auxiliary carry, overflow and parity, these are the conditional flags. The bit PSW3 and PSW4 are denoted as RS0 and RS1, and these bits are used to select the bank registers of the RAM location. As I have already told you that 8051 is divided into 4 banks and each bank is having the 8 registers denoted by R0 to R7. So in order to select any of these registers, first of all, some bank has to be selected. As the power is on or the system is reset, the default bank that is selected is bank 0. In case we want to change the selection of the bank, so we have to use these 2 bits to select the particular bank. How? So as I've already discussed, 7th is the carry flag, auxiliary carry flag, flag 0 available for general purpose, register bank select bit 1 and select bit 0, overflow flag, user definable flag, and last is the parity flag. So when we talk about these 2 bits, that is the PSW 3 and 4, the use is mentioned here. Suppose the combination 00 gives the register bank 0, address is this, and similarly the different banks are selected according to the selection of these bits, 2 bits. Now, when we talk about the memory organization, as I have already discussed that 8051 microcontroller has 128 bytes of internal RAM and 4 kilobytes of on-chip ROM. The RAM is also known as the data memory and the ROM is known as the program memory. The program memory is also known as code memory. This code memory holds the actual 8051 program that is to be executed, and in 8051 this memory is limited to 64K. So what is this? It means that this memory can be extended up to 64K. We can use the external code memory. So it can be found on chip as ROM or EEPROM. It can also be stored completely off chip in external ROM or more commonly as external EEPROM. So in this way, we are available with only 4 kilobytes of ROM, but it can be extended up to 64 kilobytes. 8051 has only 128 bytes of internal RAM, but it supports 64 kilobytes of external RAM. As the name suggests, external RAM is any random access memory which is off-chip. Since the memory is off-chip, it is not as flexible in terms of accessing and is also slower. For example, to increment an internal RAM location by 1, it requires only one instruction and one instruction cycle. But to increment a 1 byte value stored in external RAM, the number of instructions we need is 4 instructions and 7 instruction cycles. So this is how the use of external RAM makes our system slower. So that's why we prefer to use 8051 for simpler applications where there is no need to connect external RAMs. Otherwise, we use some advanced microcontrollers in which the on-chip RAM is already available. So the internal RAM is found the on-chip RAM, and it is the fastest RAM available. It's also the most flexible in terms of reading, writing, and modifying its contents. Internal RAM is volatile. So when 8051 is reset, this memory is cleared. The 128 bytes of internal RAM is organized as follows. So there are 4 registers, bank 0, bank 1, bank 2, and bank 3. So there are 4 register banks and each of 8 bits, total 32 bytes. The default bank is bank 0, and we use RS0 and RS1, a flag register, that is the PSW registers, to select any of these banks. So first is the bank, second is the 16 bytes of bit addressable area, and the third one is the 80 bytes of general purpose area, that is a scratchpad memory as shown in the diagram below. So this is the diagram. The 32 bytes of RAM from address 00 to A1F is used as a working registers. So the register bank 0 is shown expanded here. So that is 00 to 07 is bank 0, bank 1, sorry, bank 0, 08 to 0F is bank 1, 10 to 1F is bank 2 and 3, and so on. So from 20 to 2F, 20 to 2F, this is the 16 bytes of bit addressable area, and 30 to 7F, which is 80 bytes of general purpose scratchpad area. So this is the whole internal RAM shown here. So suppose we want to move R7 to A. So this is how the R7 is, the value of the R7 is moved to A. Now we want to move some immediate data to R7. So in this way we are going to execute it. Now when we talk about the internal ROM, that is it is 4 kilobytes of read-only memory, and it can be extended up to 64 kilobytes. So it is also known as the program memory or the code memory. The code segment is accessed using the program counter, as we all know that the program counter always holds the address of the next instruction, and the DPTR is used for data access. So the external ROM is accessed when the external access pin is connected to the ground, or the contents of the program counter exceeds 0FFFH, that is, a limit exceeds. So when the internal ROM address is exceeded, the 8051 automatically fetches the code bytes from the external program memory. So in this way, whole ROM is divided into 2 parts, that is internal and external, or we can completely use external also. This is our choice. So in combination, these can be total 64 kilobytes, not more than that. If we are using 4 kilobytes internal, then we can only connect 60 kilobytes. If we are not using this internal, we can here replace it with 64 kilobytes in total. So in this way, the total ROM which can be connected to 8051 is 64 kilobytes. So that's it. That's all for today's lecture, and in the subsequent lecture, in the next lecture, I'll share more about the internal architecture. Thank you so much.